Okay, I think we can get started, Larry. Today we have MSC Nastran Modules. Yep, Larry, do you want to
Okay,
start?
I am ready,
Perfect.
and thank you very much, Vicky, and thank you for everybody that's attending today. So my name is Larry Pierce, and we're going to be talking about assembly modeling with MSC Nastran and MSC Apex, focusing on MSC Nastran modules. And you're probably wondering what the puzzle pieces have to do with assembly modeling and finite element analysis. And I've chosen the jumble of puzzle pieces as the title image because assembling an FEA model is a bit like putting a puzzle together. It requires patience, a strategy, and sometimes a little bit of luck to kind of get through the mess. So our agenda for today is we're going to look at some of the current challenges in modeling assemblies and a finite element analysis. We're going to look at how MSC Nastran modules address these challenges. And modules might be a new term to you, but it sort of derives from the fact that so many structures are designed in a modular fashion. They're assembled in a modular, built and assembled in a modular fashion. If you want to think parts and assemblies, that might be another good term to use, and I will probably use the terms interchangeably in the presentation today. Modules are parts and assemblies. We'll also do a demonstration of using MSC Nastran modules in an assembly modeling workflow within MSC Apex. And then we'll have a summary and a few takeaway items. So I think the first question we want to ask ourselves is, why use assembly modeling and finite element analysis in the first place? And I think it's because most structures use a modular design approach. Once again, they're often built in a modular fashion and then brought together for assembly. That's true for the aerospace industry, where the wing might be built one place, the fuselage another place, and they're brought together for assembly, final assembly. That's true in automotive as well. That's also true in the space industry. Offshore, shipbuilding, same kind of thing goes on. And even at a more local level, I might just have a model that has several brackets that are the same, a lot of bolts that are the same, and it would be convenient to model this in a part and assembly manner as opposed to just modeling it as a monolithic model. So the current approach in finite element modeling does follow a similar approach. So oftentimes, and I'm going to use an airframe as an example, but it's similar for automotive, for shipbuilding, for spacecraft, for everything. But oftentimes, different finite element components may be built by different design and engineering teams. You may have a team that builds the nose, a team that builds the wings, a team that builds the fuselage model. Their product will be a Nastran input file with everything that's required for that portion of the model, okay? So these components are then assembled into the complete finite element model, and the most common way of doing this is called the include file method. Once again, the file for the nose, the file for each wing, they're all included into the final assembly. And once again, the result of that would be the complete finite element model. Ideally, this workflow should allow the different teams to work efficiently, right? Both separately and together, whether they are pre-processing, assembling, or post-processing. The include file approach definitely works, but it's not without its challenges. So let's kind of dive into what the challenges might be. So what are the challenges with the include file method? Number one, and probably the biggest, is that each include file must stay within an assigned ID range. So the nose, for instance, might have ID space for the nodes and elements, et cetera, of 1 through 10,000. The wings might be 10,001 through 20,000, and the fuselage might be 20,001 through 3,000. When these individual input files of each individual component are combined together as includes, okay, the assembly of include files is going to have an ID range from 1 to 30,000, and there will be no conflicts because ID conflicts are not allowed. In other words, the solver doesn't know what to do with two elements that both have the ID of 27. Which one counts? Which one doesn't count? Typically, there's not a problem in the initial stages. In other words, I've been given the task to model the wing. I know what my ID range is, and I'm going to build an appropriate model that fits in that ID range. The problem occurs when change happens, and change always happens. I mean, change really is the only constant. So whether or not I have a requirement to refine the mesh a little bit, what if I'm going to refine it so that I now spill outside of my ID range? What am I going to do about that? There could be new vehicle variants. Almost anything new or added can be a problem when it comes to managing the ID range that you have been allocated. Another challenge is that include files cannot be reused at different locations. They cannot be instanced via translation or rotation or mirror operation. So let's imagine this right wing, which has node and element IDs and has locations. What I would really like to do, assuming that the left wing is identical, I'd really like to instance it. I would like to do a mirror instance. And I would like to do that so that there's sort of a relationship between the wings, so that if I change the right model a little bit, the left one automatically updates. Well, you can manage the mirror operation with pre and post processing, but you end up with a new set of node IDs, a new set of element IDs, and honestly, you end up with a separate model, which basically means if I change the right wing, I got to change the left wing too. So the current workflow using preprocessors to make that copy, it's not an obstacle, but it is a hurdle. It is extra work. Similarly, if I want to make the fuselage larger, if I want to extend it, perhaps there's a region of the fuselage that I would just simply like to translate an instance. Once again, I can do that with the preprocessor, but the preprocessor is not an obstacle, but it is a hurdle. It's going to be extra work. It would be nice if it was an instance of the portion that I'm actually going to use. That way, a change to the parent, I'll call it a parent, would automatically mean that there would be a change in the child as well. Another challenge is that included models are manual, the connection of included models are manually managed. There's typically several meetings to decide on how many nodes that are going to be connected, what are their IDs going to be. That's critically important because we can't have ID conflicts, right? And this becomes a real issue if we need to change it, right? If we need to add a node for some reason that we did not foresee when we first set out to create the model. That's actually going to be additional meetings to communicate both upstream and downstream of your section of the model to make sure everyone is aware of what's happening. Another challenge is that the results are not modular. In other words, you get one set of results for the entire assembly. And this in and of itself is not a problem, but then it is an obstacle to efficiency because it would be better if the component teams just had the results that they need. Why lug around a whole big set of results that I don't need? Most companies will create scripts, will create additional solver runs, or some other gymnastics to parse the results into separate files for the individual post-processing teams for each component. And then another challenge with the include file method, and it's going to be the last one that I illustrate, but you may have other challenges that you are aware of, is that include files are generally not standalone. And a standalone model is really useful for component model verification. Does my model, is it really all connected together? Is its response kind of sort of what I expect? Because it's easier to debug it now than to try to debug it once it's included with the rest of the structure. Since it's not standalone, I generally have to reach into additional files for the full model definition. You know, whether it's to get those interface nodes or materials or properties or masses or RBEs, I have to go and get that from somewhere else so that I can just run my component to kind of verify it and check it out. And at this point, I have to ask myself the question, did I get the correct data for the correct variant from the correct file? And I find when I have to ask that many questions, okay, that there's a big chance that I may make an error. There's a big opportunity for errors. And that's important to me because I am accountable for my model, and I want there to be less chance of errors, okay? So MSC Nastran modules address the pains of working with include files. So how does it do that? Well, number one is you can have non-unique entity IDs, okay? So, I'm doing the nose, you're doing the wing. We both can have element number one and node number one. There's no conflict. Now, clearly within my component, I have to be unique, but I do not have to be unique across components. That's a big, big thing. What that means, I can mesh it however I want, and I'll be fine. I won't run out of IDs. The whole idea of allowing non-unique entity IDs also enables another big advantage, is that I can model a component once and reuse it at multiple locations and in multiple assemblies. As a matter of fact, the component model can be easily translated, rotated, and mirrored. All right. And I've really just got that original component. Remember my little example earlier where I wanted to mirror the right wing to the left wing, and I wanted them to be associated, so a change to the right would be reflected in the left. Well, here's the answer to that. Modules will enable that and allow that. So we know that modules are going to have to be connected, and what we've said so far is exciting, but how do I connect them together? Well, component models with modules can be connected automatically. We'll talk about that. It can be semi-automatically, or if you need it to be manual, you can. We'll talk about what the options are, but connecting modules together is honestly quite easy. And also, to help facilitate efficiency in the downstream post-processing, the components can actually have their own individual result files. So this enables component level post-processing without jumping through additional scripts or additional solver runs or additional gymnastics to get the results into a format that the different component teams can easily digest. So those are the features. What are the benefits? The number one benefit is efficiency. It really is efficient model management. Honestly, another benefit is how easy they are to connect, and that also becomes an efficient model management characteristic of modules. Ultimately, you're going to save time. And time from a corporate perspective is honestly money. And it's also the ability to get the design out the door faster, get the margins faster, hopefully achieve some sort of certification or some sort of we're done with the project faster. I think those are all corporate things. From a more personal level, I think about the consistency, the repeatability, the flexibility, and the confidence. And confidence is in my model and in my results is very important to me because I am accountable. So this helps me sleep better at night, helps me have less fret and less sweat. That's super important. So let's dig into each one of these features just a little bit deeper, just real quick, and then we'll get into live demonstration. So once again, modules do allow the non-unique IDs. No more ID range issues due to a last-minute model update, which can be painful and can be error prone. And we know that update's coming because change is the only constant. Modules allow duplicate IDs of nodes and elements and materials and properties, et cetera, between the different modules. Therefore, you no longer have a strict ID budget, and you can enjoy the full range of IDs for your component. Don't let the fact that I've only got 10,000 IDs restrict the modeling that I might need to do to achieve the results I need to achieve. Modules are easy to reuse, so it provides consistency and repeatability in the fact that I can reuse. Modules allow instancing made easy. I can model a component once, reuse it at multiple locations, as well as in multiple assemblies, and no renumbering is required. I can relocate and reorient, so modules can be moved or copied to a new location. They can also be rotated or mirrored. You're actually seeing some images from MSC Apex. We'll have a little bit more about that in a moment as well. All of the above, the non-unique node IDs, the fact that we can easily relocate and reposition, that leads to efficient management of design variants. So once again, with instancing and no renumbering, it's really easy to create and manage your design variants. Almost every plane model that comes out is going to have an extended version so we can get more seats in there. And of course, even in automotive today, I bought a car earlier this year, and the frame that car sits on is actually on other cars as well. So there's a need to actually easily create variants and have variants connected together, et cetera. Reuse components. So we hinted about connections earlier. So let's look at connections just a little bit more. So based on a proximity search, okay, a tolerance, the components can be automatically connected, meaning that if nodes between modules fall within that tolerance, they can be automatically connected. This enables modules to be relocated in instance, and effectively, they're automatically connected. Basically becomes plug and play. Now, clearly, we have to think about this a little bit, meaning that, for instance, in my little fuselage example here, I have to make sure that I have nodes at the proper cadence. In other words, I know that I've got 24 nodes around the circumference of the fuselage here, or however many nodes there might be. So a little bit of planning is required. But if I do that up front, once again, I can basically have the ability to move modules around, and it will be a plug and play connection. Now, we clearly know that at times you want more control, so modules can be excluded or included in the automatic connections. Nodes can be included or excluded. Nodes can even be manually connected, so you have full control. But if you choose, or if you create everything so they can be automatic is a potential possibility. Now, in addition to node connections, sometimes there's a need to actually connect with an element, okay? So we do provide rigid and flexible connections. So rigid might be an RBE2, an RBE3, multi-point constraints, or even an R-joint, for instance. Flexible might be a bushing, a fastener, even a DMIG. I find that interesting. So it really is just a stiffness. In other words, it's really just a flexible connection between my modules. So I have a lot of opportunity to make sure that I get the connections right so that I can get the results that I want to achieve. Even included in the connections would be contact interactions. So I can have glued contact between modules as well as touching contact. Imagine that I've got a bolt pattern, and I can have a bolt that is a module, and I can instance it within the pattern, and I can include touching or glued contact between my bolt and the things that it is connecting. So modules allows modular results, and that's important because a component may show up in many design variants with lots of load conditions, right? So the modular results can be output to a single results file, so everything can be dumped into one bucket, all right? But I can also write the results for individual components into individual HDF5 result files. Additional runs for additional variants or additional load cases the results can be appended to the already existing HDF5 file for that component. And that's significant because these component level result files make it easy for me to share results with the component teams, and also facilitates enveloping and searches within only a specific component. And by the way, since I can append results into that file, I can actually do those searches across all load cases and all variants all at the same time. I think this allows us to be faster as well as less error prone. And once again, I am accountable, and I like anything that makes me less error prone. So a question that might be in your mind right now is, I love to use super elements, Larry. Can I use super elements in a modular workflow? The answer is yes. It's called external modules, and an external module is created similar to an external super element and can be assembled into an assembly model that contains modules. So basically you get all that you love about super elements and all that you might love about modules working together. Now, this is a really good point for me to stop for just a second. And you may be saying, you may be noticing something here, right? So super elements are reduced, right? That's stiffness matrix, mass matrix, etc. Modules, on the other hand, are not reduced, right? So it is the full model. It'll have to be, resolved again. So there is a slight difference. They look a lot alike, right? But they are slightly different. Superelements are reduced and modules are not reduced. And lastly here, in terms of solution support, modules are supported in almost in actually the most common solution sequences, whether it be linear static, normal modes, all the linear dynamic solution sequences, including solution 400 for doing non-linear simulation. And we already have an enhancement list here. So we are already aware of additional solutions that people want to have modules supported in. So you might be saying this all sounds good. In other words, this is a great way of dealing with parts and assemblies in Nastran, but what about pre and post? Because what about duplicate IDs? That sort of seems to be a showstopper for many pre and post programs out there. Or is it? Okay, so we have to ask the or is it question. So the solution is MSC Apex. MSC Apex is and has always been ID agnostic. That is, duplicate IDs are allowed. So what does this mean for you, stepping into and working in a modular workflow? Well, it means I can build the model in MSC Apex. I can build the model. I can verify my component that's going to be used as a module. As I build it, I don't have to worry about IDs, right? I can use any ID space I find to be convenient. I should also point out that other pre and post processors can be used here as well, such as Patran, I'll use as an example. In other words, at this point, we don't have duplicate IDs. The next step would be the assemble step, right? This is where I read in the various modular components. I perhaps will translate them, rotate them, mirror them, and define those intermodule connections. That can be achieved in Apex because Apex supports duplicate IDs. Post-processing, I can look at the results within MSC Apex on the entire assembled model of all those individual components, or I can look at the results on just my component as well, okay? And then lastly, just simply accessing the model. There's always a need, I just need to look at it, right? So clearly Apex will let me import a Nastran model that contains modules so that I can visualize it. Perhaps I need to do some additional post-processing steps, or perhaps I need to modify. I'm going to create a new variant. So I need to translate, rotate, mirror, or update my connections. All of that is available and allowed in MSC Apex. So let's shift gears and let's do a demonstration. Now the demonstration, we have a short time frame, so I'm not doing every step, but I think I'm going to do enough steps that you'll get a feeling of the flavor of working with MSC modules in Nastran and in MSC Apex. So what are you going to see in the demo? I'm going to start out with what would be step one, which is the build step, where we'll have an individual component. We'll kind of look at what an engineer might do for a building and what advantages working with modules has for that person. We'll look at the assemble step, and we'll even go into it and look at building up variants of the assembled model. And we'll look at post-processing, because those are the areas that will be most important to us in a modular workflow. So let's do that, okay? So I am in MSC Apex, and I am looking at a wing. I am specifically looking at the left wing, and you can see that I'm actually looking at geometry right now. I'm just looking at some surfaces that represent the outer skin, the ribs, as well as the spars, etc. You can see that I've already attributed with some masses that might represent the fuel and the locations of those masses. And my purpose today is to talk about modules, but not to talk about meshing. So I've actually already meshed this. So I've got a mesh on my structure that I created that is a mesh that's appropriate for what I'm trying to accomplish. It's going to give me the kind of results that I might be looking for in this case. And once again, I've got a mesh for the outer skin, I've got meshes for the spars, I've got meshes for the ribs, and I've got meshes for all the stringers that are there as well. So the advantage of knowing that I have a modular workflow working, that this is just going to be integrated into a model with modules, is I don't have to worry about the ID space. So, yes, there is a range of IDs that are here, but I don't have to worry about it. I don't have to worry that another component is going to have node number 1 or element number 1 or node number 4477. I don't have to worry about that. So there's no concern about the ID space. I don't have to think about that at all. Really, the only thing that I might want to think about is how this might be connected, right? And in this case, the spars are going to connect to the wing box. So I probably need to think about how that connection is going to occur. Is it going to be node to node? If it is, I want nodes in the proper location, but I don't have to worry about their IDs. Perhaps it might be glue or some other technique, or even some sort of element like a bushing, but I just need to kind of think about that a little bit. That's something that I would have thought about anyway, okay? The last thing that I might do is, once again, I want to verify my component, right? Is my component all connected together? Did I forget to quote equivalence or merge nodes? Or if I was using glue, did I actually forget to do the glue part, right? So because modules are completely self-contained, everything I need is here, okay? I don't have to reach into additional files, which once again, when I do that, I'm always asking my question, am I getting the right data from the right file at the right time? And anytime I have to ask that many questions, I really think that leads to the potential for errors. And once again, I am accountable. So, I just did a simple modal analysis of my wing, and I'm just expecting to look for modes. I don't have any constraints, so I actually have 6 rigid body modes. This is the first flexible mode, which I would expect it would be some kind of bending mode like this, clearly, right? So I can run the model. In this case, I chose to do a modal solution, but I could also look at other solutions as well to get a feel for, is this exactly, am I meeting my objective? At this point, I would export this to a Nastran input file, and we're now ready to go to step 2. And step 2, we're actually going to do the assemble step, okay? So I'm going to start the assemble step with an empty MSC Apex database, and I'm just going to go File, and I'm going to go Import, and I'm going to import a Nastran input file for the nose, okay? So I'm going to import that nose of my airframe, of my air vehicle. So it's going to come in. I like to always check for errors and warnings. There are none. So that means I did a good job. So here is the nose. And we can sort of look at it here. If we look sort of the inside and let me shade it, it'll show up a little better. I can see that I do have a skin. I do have some frames. I can turn on some data, and I can see that I have some stringers and some caps. So I have everything that I need for this to be a model that meets my requirements. I am going to assemble a model of Nastran modules. So the first thing I will do now is right mouse button and create a primary module. And a primary module is different than a secondary module, which is effectively a copy. In other words, like when I mirror the wing, that is a secondary module. So let's create a primary module. Apex says, well, you are about to assemble a module. Are you really wanting to do that? I said, yes, I really want to do that. So I've got a module. I can look at the module and I can see that it's currently going to connect automatically. I could clearly change that to manual. I can also define some boundary nodes that I want to include or exclude. I'll leave all that as it is for the moment. Let's read in another module, another component. So we're going to import the radome this time that's in the front. So I will select the radome and we'll import it. And no errors or warnings, so we'll bring that in. And Apex is saying, I detect duplicate IDs. Do you really want duplicate IDs? Now, if I was doing a traditional finite element thing where non-unique IDs are not allowed, I would absolutely say offset. But I'm doing modules. I'm going to accept the duplicates. And I think that's important because the person who did the radome maybe counting on certain IDs to be in certain locations because that may facilitate some downstream post-processing. So I really don't want to change those IDs. So I'm going to import and accept the duplicates. So now I've got the radome. It's not currently a module, but I'll right mouse button, see how easy it is to make a module. And now it is a module, okay? This is where we have to think about how the modules are connected, okay? It's clear that I have had a meeting with the radome person and we agreed on the node locations for the connections. And if we look at each one of these, it's set up to do an automatic connection within a particular tolerance, which effectively means that because these nodes share common locations, that's where I'm going to have my node to node connection, okay? Speaking of nodes, speaking of IDs, let's look at the ID space because we were told that we have duplicates. So the question is, do I really have duplicates? Okay, so we're going to go look for a node number 1, and we'll look for node number 1 in module number 1, which would be the nose part here. So we will find it, and there it is. Notice that we have 2 IDs here. One represents the module, one represents the node. Now let's go look at number 2, all right? And we also have a node number 1 here, perfectly acceptable in a modular workflow with MSC Apex and MSC Nastran. So at this point, we've done a great job. I could continue reading in the individual components, but I've already kind of got the rest of it all strung out. So let's go and import that now. So I will import. This time, I'm actually going to import a model that has modules in it, but it's just the modules that I'm missing. So we'll go ahead and import those. So now I will have a lot of modules that make up the remainder of my air vehicle, my airframe here. So you'll see a bunch of modules show up in the model browser in 1 second. All right, there they are. Let's kind of clean up the display a little bit, and let's talk about a few things that we have here. All right, so I do have a lot of different modules, right? I've got my nose and my radome, but I've got my nose and my radome. I've got that. I've got various other things in here as well, right? So I've got all of those things in here as well. So here we are. We've got all those different things that are there. I want to talk just a minute about additional connections, all right? So let me go to a transparent view. So we'll go transparent here. So we've talked about automatic, but automatic is not the only option for connections. So here, I've actually got a bushing that is doing a node-to-node connection because maybe I want a particular stiffness between my connection. I don't want it to be explicitly node-to-node. And I've also got like an RBE2. These are just for show. They're not, you know, I made those up just to kind of illustrate that you have opportunities for a lot of potential connections between your modules. Automatic is just one opportunity or one option, but you can actually connect things with bushings and RBE2s. I can even do manual. So we can look here, if I hover over the module boundary connections, you can see some nodes highlight. Those are some manual connections if I really want it to be manual. You have a lot of options when it comes to connections. I can do touching contact and glue. I can do RBE2s and RBE3s. I can do connectors like C-bushes, etc. So we have a lot of options when it comes to connecting the modules. So you'll have complete control to achieve the objective that you would like to achieve. So my structure is not really yet complete. So I need another wing. I don't think it's going to fly the way it is. So I'm going to right mouse button on the left wing, and I am going to create not a primary module, but a secondary module. Okay, it's derived from the primary module. And at this point in time, I definitely have a copy, but it's not very useful because it's positioned where the original was. Let me at least give it a different name because it's going to be the right wing, okay? But I clearly want it to be in the proper location. So I will come in and I will go to the properties for the right wing. It's an automatic connection. Remember, it's going to be connected where the spars connect to the wing box. And I'm going to do a transformation. So I will add a transformation. I'm going to do a mirror operation. And my mirror operation is going to be with respect to the XZ plane. I'll hit the green check, and there I am. I've got both a left wing and a right wing. I think I might have an opportunity to fly now. So we could consider this our baseline configuration. And if it was our baseline configuration, then we would probably want to export this and do an analysis with it. So let's look at what happens when we do that. So I'm going to create a new scenario in MSC Apex. I'll call it baseline, and we'll say okay. I will add the model that I want to analyze, which will be the model that I have. And I'm just going to look at two things here because I want to mention two things here that I think are important. When I export the Nastran input file, I get an opportunity to export a flat file, which basically means all the modules will be in a single file. They'll still be modules, but it's all in one bucket, okay? That's useful. But what I think is even more useful is if I write each individual module to its own bucket, okay? And what makes this even better is typically each module will be in its own file anyway, all right? Well, if I'm actually making modifications here, then when I export, I don't have to export any module that did not change. So Apex gives us the opportunity. I really think this is a great way to manage things and to make sure that I'm not duplicating effort, helps me maintain an association to the proper file. Only files will change if they really change. So I don't have 12 files for the wing when I really just need one because it's not changed. I think that's a significant thing, and Apex will help you manage that. The other thing I want to mention is we've already highlighted the fact that the result files can be in a single file, but I can also do it on a module by module basis. So Apex will let you control that. The default is a single file for all, for everything in one, but I can also have one result file per module. I can even have one result file per module, and I can control the name. One, by default, Nastran will control it, but you have the option to control it if you want to as well, okay? So that would be a typical workflow of importing some modules, connecting them together, and exporting. In this case, we exported our baseline configuration. Let me go back up here. We'll turn transparency off. Let's say, pretend for a moment that we're now ready to do the next variation, all right? So in this particular case, we're actually going to translate. We're going to translate some of the modules that are at the tail so that we can have an extended fuselage version of this. So I'm just going to extend it by 24 inches. There we go. I've left a gap that I'll need to fill in now. If I go look at, for instance, the aft fuselage knows that it's being transformed. I should point out that although Apex is doing the transformations for me so that I get a visual image of what happens, this actually occurs in Nastran. So that's a nice feature as well. So I want to do one more transform. I'm going to pretend that this section of the fuselage is really going to be it's going to be the same. So I'm going to create an instance. So I'll take that one and I'll move it 24 inches. And I have filled the gap. And I also now have a new secondary module for my extended fuselage, okay? If we look, we'll see that it's automatic connection. And automatic connection will be fine because I have taken care that I know exactly how many nodes I have around the circumference of the fuselage, and I know their location. If that was not true, then I would need to actually look at some of these other methods of connection, all right? So let's keep going. I'm now going to assume that there's going to be a belly pod underneath that represents maybe some electronic equipment, surveillance equipment perhaps. So let's go and import. We'll import the belly pod. And here's the belly pod. And it comes in, and voila, I have a totally new configuration, one that has the belly pod. I could read in many belly pods if I wanted to read in different configurations of the belly pod. It's currently set up to be a manual connection, but I could make it automatic. Or once again, I can use any of the other things that are at my disposal for connecting this module to my structure. In this particular case, automatic would work because I have made sure that the frame that's in the belly pod will connect with the frames that are on the fuselage. So I just planned for that. That's where they would connect anyway, so I knew that that was coming. I want to make one more modification before we run on to post-processing. I will import one more. I know a lot of these UAVs will have an air duct on the end. So just for visualization purposes, I created an air duct, which, oh, I brought in a belly pod instead. So let me breathe in I clicked the wrong file. So here we go. We're bringing that air duct, the air intake. So we'll import it. And there it is. And in this particular instance, I just made that air intake for show purposes. It makes a nice picture. But if I wanted to run that with the rest of the model, in this particular case, none of the nodes line up. It wasn't really designed that way from the beginning. So how can I connect this to the rest of my structure? I'll just go and I'll just glue it, okay? So we can go to the interaction tab, and I will select this component, and I'll select this component, and they are glued. You can tell it's glued by the color coding of the elements. Apex automatically color codes so that a priori you know which elements are participating in the glue. We clearly see there's no glue back here though. Well, that's because this is a different module, right? So the gluing is on a module by module basis. So we'll show only, and I can see that I'm glued both to the module to the front and I'm glued to the module to the rear, and I can see exactly which elements are participating in the glue based on the tolerance that I have entered. So at this point, we have built a component. We have also assembled components. Let's look really quick at post-processing. So Apex allows me to post-process all of the structure, the entire assembly, okay? And I do believe that the engineer who built the assembly would absolutely want to do this. So I actually can look at displacements, I can look at stresses, I can look at anything that I might want to look at to make sure that everything is connected and to make sure that maybe the results make a little bit of sense. Perhaps I know what the maximum wing tip displacement should be for this load case, and I would have a feeling that everything is correct. I can even go so far if I want to, and let's turn off the fringe plot in this case. You know, I can even go so far, this would be equivalent to this being an internal loads model. I'll show the right wing only, so we'll show it only, and I will set it as my plot target. And perhaps what I'm really interested in here are the interface forces at the spars. I'm interested in what those loads are at the spar, between the spar and the wing box. And I absolutely can look at those, see where those forces are. And I absolutely can, you know, if I want to know what the actual values are, I can clearly label them. So I think that would be something that might commonly be done by the person that was assembling this model. And of course, many times, even these numbers might be the numbers that need to be distributed to the different component teams. So this was post-processing the entire assembly. I might also want to post-process an individual component. So here I'm looking at the left wing. I'm the engineer that this is my model, and once again, I'm accountable for it. I can look at the results. In this case, I can look at the results for the baseline, but I can also look at the results for a stretched version. So I'm actually looking at the results from two different variants simultaneously. If I wanted to compare these results, I absolutely can do that. I typically think that the component level engineer, in addition to looking at like aggregate numbers like overall deflections, et cetera, I think they would also find themselves wanting to look at some more localized results. So I might actually go to an individual rib and show just that rib, and let's set it as the plot target. And the common kind of thing that I can see the component level engineer doing is perhaps, looking at the free body forces that are there. So now I'm plotting the free body forces that are acting on the rib from the rest of the structure. So I think that's another thing that that engineer would do. In the interest of time, I'm gonna go back to my presentation, but we went through effectively the entire process. And so we know, though, that that's not the end, right? That's not the end, because we know that change always happens. We know that problems almost, I wish they didn't always arise, but they arise quite often. And so, and by the way, what I'm about to talk about, if you actually want to see a demonstration of it, I've got a link here. You can go to that link and actually see a demonstration of everything I'm about to talk about. But let's just imagine for a minute that there's a problem in the aft fuselage, right? So now that there's a problem in the aft fuselage, we might want to do a global local model. We want to create a more refined version of the model in the area of the problem. So the engineer, rather than having to kind of digest the entire model, they just digest the module, right? They digest the module for the aft fuselage. They import some geometry in the area of interest, using that geometry to create a detail representation in that area. Since this is a module, I might also choose to actually modify the mesh for the module, maybe because I'm going to do some gluing in this case. Now the mesh densities are a little bit closer, not quite as disparate as the overall global to the overall local. So I have that opportunity because it's a module. It's very easy because, once again, this is self-contained. And since it's self-contained, I can actually do a quick, in this case, I did a modal analysis because I was using some glue. And I'm just making sure that everything is connected, right? Now the glue, I know the glue is operating properly. So I'm now ready to replace the original aft fuselage module with the new aft fuselage module that has my local model in it, right? Now I can get the local results that I need to ascertain what problems I might need to do something about, that I might need to address. You'll see if you watch the video that we actually used glue because the aft fuselage now has a different mesh density than the rest of the structure that it connects to. Before, that connection was automatic. Now it's going to be a Nastran glue, okay? And once again, I will end up running the entire model. Matter of fact, I might even want to make these other portions as external modules, right? That would be a great thing to do. But I can look at the results on my individual module and make a judgment. Am I actually addressing the issue I was trying to address? The nice thing about modules is if we have other design variants, I can plug that same module and see if we have that same problem in other design variants that are out there. And it's plug and play. It's really that simple. As I pointed out earlier, model management is super easy with MSC Nastran modules. So what are the summary and the takeaways that we might have? Well, I think the summary is that we saw a full vehicle analysis process with MSC Nastran modules today. We know that at the build stage that engineers no longer have to worry about the IDs. We know that verification of the model is easier because my component is self-contained. We know that connections still require a little bit of coordination, but hopefully it's less meetings now than it was before. The assemble stage is a breeze. I don't have to worry about IDs anymore. Connections are very flexible. I have a lot of options that are available to me, whether it be automatic, semi-automatic, or manual. And modules, the individual components are multi-use, and I can use them in multiple variants. So this assembly process is super efficient now. And lastly, post-processing has the advantage that now the results are component level, okay, and appendable, so that I actually can have results for my component for multiple locations and multiple variants all in one common convenient location in the same file. So that's the summary. I hope the takeaways will be that modules are ID agnostic, they're multi-use, they're multi-location, think instancing. I can work with multivariants, I get component level verification, and I get component level results. I think all of those things really tie into the fact that using modules is a very efficient model management paradigm. I think those will help the program um, get results faster, get margins faster. It'll save time. It'll save money. I think on them, I always like to think things at my level as well, because I'm an engineer as well. I like for things to be consistent. I like for things to be repeatable. I like for things to be transparent, and I like for things to be flexible. Once again, I am accountable. These things help me achieve less fret and less sweat. And the last takeaway is we've shown a lot today. It's all supported by MSC Apex. You're free to edit the bulk data files if you want to, but I can do all of this in MSC Apex and visualize and make sure that all my I's are dotted and make sure that all of my T's are crossed. That is all I have to share today. I so appreciate your attention, and we have a few moments if there are some questions.
Larry, we have replied most of the questions. I think one that just came is, what is the earliest version of MSC Nastran that accepts modules? I don't, maybe you can answer that better. I think it's 2018, I would say, or 19, but I would let Larry confirm that.
I am positive it's 2018. Yeah, I'm pretty
2018, yeah,
positive. Yeah,
perfect.
yeah, I'm positive it's 2018. But
Yeah.
some of the features that we've talked about are not available then. For instance, if you want the results to be in an individual HDF5 file, that was not available in 2018, and the ability to append to that file was not available in 2018. Those are more recent additions to modules. So, good question
Exactly.
though.
Are rotor dynamic capabilities supported by MSC Nastran modules?
The answer to that is yes. I'm not sure that every capability, but I do know that the answer is yes. So,
How can we make sure that automatic connection worked well?
so there's several ways to do that. But Nastran itself in the FO6 file will actually give you a really nice table that shows you everything that is connected. And it will actually go so far as to tell you if it was a manual connection or an automatic connection. So I think that's a great visual to give you the confidence that everything is connected as you would. I don't have that ready to show right now, but you do get a really nice table that shows that.
Okay, I don't think we have more questions, Larry. Uh, so thank you for today's presentation. I think we can close this webinar. Thank you everyone so much for attending today. The video will be posted on YouTube as well, so you'll have the option to rewatch this one. So thanks a lot for today. Yep, and bye.
Okay. Yeah. Thank everybody.
Bye.
Bye.
Thank you, everybody.